Hi, I'm Chris Brown, and this is the second lecture in a series on axiomatic design. It's part of a grad course on axiomatic design of manufacturing processes here at WPI, Worcester Polytechnic Institute, where I'm a member of the Mechanical Engineering Department. So in the first lecture in this series, the first module, we asked sort of what is design? And now the question is, what is a good design? So how do you tell if a design is good? Now when I asked this question in class, people usually answer something about cost and function. And is there a cheaper one that's going to do the same thing? And sort of how much does it cost? Now, cost is difficult to assess before you design something, and so is sort of functionality. So how do we know if it fulfills its functions? That's another aspect of design. Is it good? Well, it has to fulfill its functions, and the cost has to be good. But the question is then, the important question is, how do you know if it's fulfilling its functions? Now, the functionality is key. If it doesn't fulfill the functions, then it certainly isn't a good design. We really don't care how much it costs if it doesn't fulfill the needs, doesn't satisfy the needs. So how do you know? Do you have to build it first to find out? This is expensive, takes time, and delays time to market. Is there some way that you can measure or assess the probability that it's going to fulfill its functions before you make it, while you're designing it? And how early in the design process could you tell? Another kind of way to get at this question, what is a good design? So who do you get to judge a design contest? Now we have lots of design contests, and people enjoy judging them, and students enjoy participating in them, so I don't want to critique those. But let's look at this critically and objectively. How do we know if somebody can evaluate designs? Usually we're looking for experience. So this would indicate, as we discussed in the first lecture, that the way we practice design now, engineering design, is largely an experiential kind of discipline. It's more of an art, perhaps, than a scientific discipline. What are the criteria for evaluating designs? How objective are these criteria when you're judging a design contest? Now, it's not that it's terribly important that we train people how to judge design contests. But judging a design contest is kind of the same as doing a design review. So when we're sitting in on a design review, and we may be in a position where we're responsible for selecting which design to invest in, or we are trying to direct where we're going to put our resources in the design, or we're just part of a group of engineers that are trying to then say, all right, which design are we going to show to management or to the next level up in engineering? So how do we know which design is good? So it's a kind of design contest. How can we be sure that the criteria we're using are objective? So how do we tell which designs are the best? Do we have some way of measuring the quality of a good design? Now, in industry, most engineers tell me that the way their designs are assessed is largely by, did you get it in on time? Did you meet the deadline? And sadly, and managers pay attention to this, the engineers go around, especially ones that have just entered the workforce, go around and get a bunch of signatures from people that are too busy to look at what they're signing. Nobody critically evaluates the design in any kind of meaningful way, but the only thing is, did you get it in on time? How do you assess the functionality, and were you able to achieve it? Can you quantify the probability of doing it? Can you predict whether it's going to be functional? And how early in the design process can you do that? And that's important, because if you can't do this early in the design process, then you've got to, perhaps you're going to be investing in some avenues that won't be productive, in developing some designs that you're going to have to abandon later when you can do a better job of selecting which the best one is. Now, often when we're doing designs and reviewing designs, we find that people are passionate about their particular design solutions. People really like to see their contribution in the design solution. This is normal. But this kind of passion can often lead to prolonged and unproductive discussions. We have to recognize that if we don't have objective criteria, designs are very much like babies. They tend to look good to the people who made them. And as I said, this sort of tendency to want to see your design represented, or your portion represented in the final product, can lead to prolonged non-productive discussions unless we have some kind of objective criteria, some sort of rules for the game. Now, as we ask sort of what makes a design good, quite often people come up with the KISS principle: keep it simple, stupid. Simplicity, I would agree. This is important. Now, a scientific discipline has a few self-consistent rules that we can apply to solve a wide variety of problems. What about designing the design process? If we use simplicity as our measure of a good design, how simple is that to apply? Why do we favor simplicity? Well, the fewer things there are, the simpler they are, fewer things can go wrong. So simplicity can be good for assessing functionality. So success is defined by fulfilling the functions, and if it's simpler and there's fewer things that can go wrong, then it's going to be better for, it's going to be more robust, and maybe better for adaptability or adaptation in situations. But this is the problem. Is the application of simplicity itself simple? Is it self-consistent? And so if we think about trying to assess, even if we're just going, say, to purchase a lawnmower, which one is simpler? This may be very difficult, particularly if the lawnmowers have got similar kinds of features. But certainly they must be different if different people have manufactured them and designed them. How do we assess that? Now imagine if we're trying to select an airplane. Now, how can something be made simpler? In particular, how can our selection criteria based on simplicity be made simpler? Because that's what we're trying to do now, is understand the design process. And to do that, we need to understand how we can assess or evaluate designs. So, when we have a big problem, the idea is to decompose it, and decompose it until the solution is obvious. Now, axiomatic design decomposes simplicity, this simplicity directive, if we want to call it that, into two parts. Maintain the independence of the functional requirements. This means that the design can be adjustable, controllable, and avoids unintended consequences. All good things, essential things for good designs. and then minimize the information content of the design. Now this is axiom 1 and axiom 2. Now, as we will see as we develop this, if we minimize the information, there's less to explain, and this makes the design also more robust, allows us to use larger tolerances, and maximizes the probability of success. So we'll talk more about these both. But as we talk about robust and robust in the face of change, we also talk about adjustability. Why is this so important? Why is accommodating change so important to design? Why is it fundamental, essentially, to design? Well, change is everywhere. Change is ubiquitous. Nothing is constant, as they say, except change. The universe is not in equilibrium and won't get there. Something is always changing. Weather changes, people change, people's needs change. Functions need to be adjusted. Now, if we think about the design process itself, and anybody who has ever worked in industry knows that during the design process itself, the design changes. Almost never. And I have never found anybody working in industry who says this, that they were given a design problem and then left alone with those design criteria to fulfill until they were completely finished. Changes always are coming in. So we need to design process itself that can be adjustable. But let's get back to change. Why is change so important? Well, because it's everywhere. Then why is calculus so important? Well, calculus models change. dy dx. This describes how one thing changes with respect to another. This is what Newton and Leibniz were thinking. How do we describe change? And that's so important that calculus, differential calculus, was essentially developed to deal with change. Alright, so we have the axioms, and we're going to be developing this. But what other method would people use? What else might you do for your design process? Well, algorithmic design is probably the kind of design that most people follow. And this emphasizes the steps to follow. Frequently in industry, there's a series of criteria that need to be met. Have you done this? Have you done this? Have you done this? And many of the textbooks, I would say most of the textbooks, if not all of the textbooks, say here are the steps that go into design. And it might look something like this. Define the problem, and study the problem, brainstorm, come up with some ideas, choose, who knows how, the best solution, build one, test one, communicate the solution, and then redesign it. The iteration is built into the process. And so, if you could avoid these iterations, if you could somehow choose the best solution with confidence so that you didn't have to build it, and it somehow goes from choose to build without the design. The design is happening someplace in choosing the best solution and building it. In between steps 4 and 5 is the whole design process. That is, if we can choose early enough in the design. Anyway, so built-in iterations. And while you're iterating, you're incurring expenses and you're delaying time to market. Don't do any more iterations than you have to when you do design. Maybe you don't need to do any. Alright, so that's algorithmic. So the algorithmic approach assumes that a correct process yields good results. And that's all it can really do. It defines an algorithm, it defines a process, it defines a series of steps. And if you do those steps well, then the design must be good. But if the design is good, then why does it just feed back into redesign and then define the problem again? It's nice, it means you're never out of a job, unless your company goes bankrupt. Because you're iterating on poor designs because you can't tell which one is better. back in step 3 or 4. All right. So if I do it right, it must come out all right. That's the assumption. But as we saw, this requires trial and error, because there is no thing in the algorithmic design that really tells us, are we on the right track? And so the evaluation is largely done by experience, kind of like designing mechanical systems before Newton. There's no guarantee of arriving at the best solution, or even a good solution, even if it's not the best. All right, so what's the difference? Axiomatic design provides the axioms. These are rules or laws that apply to all good designs. And then structure and process. And those are going to be developed in the next modules. A structure and process for applying the axioms to the design. So axiomatic design provides a means for selecting the best design solution for a set of functional requirements. And that's what we're going to be concentrating on. So this is supposed to say axioms, structures, process. So it's close. The axioms require a structure so that they can be applied. And the creation of the structure requires some process to create it. So these are topics for the forthcoming modules. Now, we can take a look too, as we're saying, decompose makes things simpler. All right, if we decompose, how do we decompose axiomatic design? Well, part of it certainly is the axioms. This is what makes it special. Without the axioms, it's not axiomatic. And these are sort of maximize or maintain independence and minimize information. And then the structures. Well, we'll take a look at this, but there's two kinds of decomposition: horizontal into domains and vertical into levels of detail. And then the process. How do we do this? Well, they will learn a zigzagging method for decomposition, and then after it's all decomposed, it needs to be integrated into a final solution. So axiomatic design. It's a rational process. It avoids unintended consequences systematically, maximizes the probability of success. It has a structure that improves communication. So earlier we noted that engineers have to communicate their design and have to be able to build a consensus among the stakeholders. So communication is essential. Now here's something I would like to suggest and test it. I think every problem can be cast as an engineering design problem. And since axiomatic design appears to be the best approach to solving engineering design problems, that means that it should be the best approach to solving any problem. Quite a claim. Quite a claim. Try it. See how it works for you. All right, where did axiomatic design come from? Well, in the late 70s at MIT, Nam Su and a group of graduate students were looking for commonalities in good designs. What do all good designs have in common? And they came up with about 17 different things, and then worked on this list and got it down to just 2 axioms and then some corollaries and theorems. Now, Nam is originally from Korea, studied in the United States, became ME department head at MIT, then engineering director at the U.S. National Science Foundation, then returned to Korea to become president of KAIST, the Korean Advanced Institute for Science and Technology, during a period when it went from 20th in Asia to 2nd. Since I'm from WPI, I would also like to note that WPI was the first of many institutions to award Nam with an honorary doctorate. Now, the premise in axiomatic design is that good engineering is based on self-consistent axioms that lead to the best solution. And this is quite a premise. We're used to this in mechanics and thermodynamics. We're so used to it that we don't even think about what it is. However, can design be like that? Anyway, I recommend watching his keynote address from the 7th International Conference at Axiomatic Design that was held at WPI in June of 2013. And there's an address for that, so you can watch it on the web. Some references. These I would recommend. These are the 3 books that Nam has written that address axiomatic design. The first that came out in 1990, and that was the same year I started using it here at WPI for teaching, is an excellent description. It's a challenging book in many ways. I admit I had to read it 3 times before I felt I could teach from it. Then Axiomatic Design Advances and Applications has got many good examples in it and develops axiomatic design well. The Principles of Design, the first one, also has many good examples. And then Complexity, Theory and Applications. And this, even though it doesn't mention design in the title, is essential to complexity and dealing with it in engineering. And it's an important book on design. I recommend all of those. So, how do we tell a good design from a bad one? The axioms. These are objective criteria for evaluating designs. It allows us to avoid prolonged, non-productive discussions and iterations. Rationale for using AD? You get better, faster, and cheaper design solutions. You work smarter. In fact, it's been shown that axiomatic design, using axiomatic design, appears to reduce the design time by 50%. And this is a consequence of improving communications and being able to focus on the best solutions early in the design process. So, also axiomatic design, as we will learn, provides metrics for progress. How can you tell how far along the design you are, and how can you tell how good the design is? Helps us to communicate design intent. That's important. We could make another Saturn V moon rocket because we have the blueprints, I'm told. But we couldn't change it because the design intent has been lost. It wasn't recorded with the design. And it helps us to develop, as we've said, the best design solutions. Thank you very much for your attention.